hope you can hear me. So yes, this is in truth a talk about the inverse renormalization group, and machine learning is a small but important part within this talk, at least with our current understanding of the method. So the structure of this talk is that I will first start by describing the standard renormalization group, which we are all very much familiar with. I will then be introducing the inverse renormalization group method, and specifically I will directly contrast it with the standard renormalization group, which will hopefully clarify the concepts. I will then give you a specific example of the inverse renormalization group for the phi to the 4 theory, and I will conclude this talk by answering the question, could we ever use the inverse renormalization group to surpass a supercomputer? So of course, someone could ask me, why should a lattice field theorist be interested in the inverse renormalization group? And of course, different researchers have different interests. I'm personally interested in it because I see it as a theoretical challenge. It goes against my physical intuition, and I want to understand how and why it works. But for people oriented towards applications, the answer is that a lattice field theorist should be interested in the inverse renormalization group because we can generate configurations of increasing lattice size without the critical slowing down effect. So I'm going to start by describing the fundamental concepts behind the standard renormalization group. So this is a configuration of the Ising model, which has been drawn in the vicinity of the phase transition, which is something that you can verify because we have some clusters that have formed. And we are now interested in applying a standard renormalization group transformation on this configuration. So what we are going to do is we are going to separate the lattice into blocks of size 2 by 2. And we are going to select the rescaled degree of freedom based on the majority of the spins within each block. When the number of spins is equal, we are going to make this choice randomly, arbitrarily. So here you can see the application of a standard renormalization group transformation on this configuration. And specifically within the clusters, you can see that some of the fine details have disappeared. But nevertheless, these two configurations look very similar to the human eye. And the first important observation is that by applying a standard renormalization group transformation, we are reducing the lattice size by a factor of 2 in its dimension. But as I mentioned, the original configuration has been drawn in the vicinity of the phase transition, and this means that it encodes a certain correlation length psi. And because we are reducing the lattice size in its dimension, this also means that we are reducing the correlation length by an equal factor. Of course, we know that the correlation length is a quantity that arises dynamically as we approach the critical fixed point, and at the critical fixed point, it diverges, it becomes infinite. So because these two systems are described by different correlation lengths psi and psi prime, this means that they have a different distance from the critical fixed point. So what this means practically is that these two systems are also described by different inverse temperatures, beta and beta prime. So it's not only the correlation length and the lattice size that is different, it is also the inverse temperature. So to give you exactly the same physical intuition in terms of a figure, this is a figure of the correlation length versus the inverse temperature. And if we run a Markov chain Monte Carlo simulation below the critical fixed point, then we have a certain correlation length that is encoded by this red circle. Then by applying the standard renormalization group, we are reducing the correlation length, and as a result, we drive the system towards the 0 inverse temperature. And if we are above the fixed point, then again, we are reducing the correlation length, and as a result, we drive the system towards the infinite inverse temperature. So the standard Monte Carlo renormalization group method is actually a powerful technique to study phase transitions. And the first reason is that finite size effects can almost be eliminated, which means that we can get accurate calculations on very small lattice sizes. And the way that we reduce finite size effects is by conducting the calculations on two systems of identical lattice size. Locating the critical point is something that can be achieved self-consistently in this method, and again on smaller lattice sizes due to the reduction of finite size effects. However, the method has a limitation. It can only be applied for a finite number of steps before the degrees of freedom vanish. And the question that I want to answer today is, can we devise an inverse renormalization group approach that retains all of the benefits of the standard renormalization group, so we are still able to partially eliminate finite size effects, works for systems with continuous degrees of freedom, which is of course important for us, that it produces the correct fixed point structure, and as a result gives rise to inverse flows in parameter space, and finally can be applied in principle for an arbitrary number of steps while evading the critical slowing down effect. And the answer is yes, we can do this, but of course it's non-trivial. And the first problem that we run into is that in the inverse renormalization group case, we must be introducing novel degrees of freedom within the system, which is of course complicated. And just to give you the physical intuition, let's assume that we have the Ising model, we have an original degree of freedom, and we are interested in inverting the majority rule. So the good news is that we can explicitly write down all of the possible risk-scaled degrees of freedom, so we have a finite, countable set. But at the same time, this does not mean that the inverse renormalization group method is easy in this model. Now, if we move to systems with continuous degrees of freedom, for example, the 5 to the 4 theory, and if we assume that we have this original degree of freedom and we are interested in inverting a simple summation, then we instantly realize that we have an infinite number of possible risk-scaled degrees of freedom, and things become much worse when we realize that these risk-scaled degrees of freedom can look dramatically different between them. So what this practically means is that even if someone won't be able to think of a transformation, it is highly likely that if we apply it 2 or 3 times, we are not going to get a system that will look like the 5 to the 4 theory at all. So it's too complicated, but it's exactly the point where we hope that we can use machine learning to solve this problem. And the main idea is that we can learn a set of transformations in the form of transposed convolutions that can approximate the inversion of a standard renormalization group transformation. So we start with a certain system that we have simulated at a certain lattice size. We apply the standard renormalization group method, and then we use machine learning to learn the best approximate inversion of this standard renormalization group transformation. And I want to give you the intuition of what it means to apply a set of transposed convolutions. So if we assume that we have an original lattice size, and we have a filter that depends on a set of weights, then if we apply the transposed convolution, this is what the mathematical operation looks like. And the idea is that we want to learn the best values of W's that are able to best approximate the inversion. And of course, we don't have to apply only one transposed convolution. We can apply 100. And at the same time, we can also supplement this with nonlinear functions to increase the expressivity of the machine learning algorithm. And the benefit in principle, which I'm going to discuss, is that we can apply this set of inverse transformations because it doesn't depend, they don't depend on the lattice size. We can apply them as many times as we want while evading the critical slowing down effect. So now we're going to discuss what it means to evade the critical slowing down effect with this method. So let's assume that we have run a Markov chain Monte Carlo simulation for a very small lattice size, let's say L equals 6, where it is easy, even if we use the Metropolis algorithm, to obtain minimally correlated configurations. So what we do is we obtain a set of minimally correlated configurations to which we apply the inverse renormalization group. So we are then able to construct some configurations of a larger lattice size. At this point, you can understand by intuition that this has the potential to be better than, let's say, a cluster algorithm, because these configurations look like as if they have been obtained via multiple iterations of a cluster update. However, this is exactly the point where someone can say to me that, okay, these configurations are representative of, maybe representative of a system at a larger lattice size, but they are approximate, they are not exact. And we work in lattice field theory, So we might be wanting exact configurations. At the same time, this is the point where a mathematician could say that we don't have a unique inverse in the renormalization group, so we can't really trust these configurations. However, as a computational physicist, it is extremely easy to solve this problem. And what you have to do is simply take these configurations and propose them as proposed configurations within a Monte Carlo approach. And if you get them accepted, then you know that you have something that is Boltzmann distributed according to the distribution that you are interested in. Another approach, of course, is to introduce reweighting as a correction step to correct these configurations. So thankfully, due to Monte Carlo simulations, we don't have to worry about the fact that we don't have a unique inverse. And now to be a little bit more practical, we can apply this set of transformations to increase the lattice size based on a rescaling factor of 2. And as I mentioned in the beginning, every time that we change the lattice size, we are also changing the correlation length. So what does it mean to change the correlation length in the case of the inverse renormalization group? So before we were reducing the correlation length, and as a result, we were driving the system far from the critical fixed point. And now, by increasing the correlation length, we will be driving the system closer to the critical fixed point. And we know from the theory of phase transitions and the theory of the renormalization group that at the critical point, the correlation length diverges. It becomes infinite, and intensive observable quantities of original and renormalized systems will become equal. So what this means practically is that we calculate observables for original and renormalized systems, and if we find an intersection, then this corresponds to our critical fixed point, which is exactly what you see here. So the implementation of the inverse renormalization group in the phi to the 4 theory is that we first apply the standard Monte Carlo renormalization group method in the system. So this is the magnetization versus the squared mass. You can see that we have an intersection which corresponds to our fixed point, and we also have the proper renormalization group flows in the system's parameter space. So now that we have verified that the standard Monte Carlo method, Monte Carlo renormalization group method works in this system, we are going to approximate its inversion with machine learning. So we expect that the inverse transformation will be equally successful. And what we do is we start from a certain lattice size, let's say L equals 32, and we apply this set of transformations until we obtain a lattice size of 512. And here you can see the results. So the solid lines correspond to an original system, and the dashed lines correspond to an inversely renormalized system. And we have exactly the behavior that we anticipate for the inverse renormalization group. So we have an intersection of observables, which corresponds to the fixed point, and we also have inverse renormalization group flows in the system's parameter space. Specifically, when we are below the fixed point, the inversely renormalized magnetization is smaller than the magnetization of the original system, because the renormalized system has been driven towards the critical fixed point. And again, the same behavior can be seen when we are above the fixed point. So can we now use this method to calculate something of interest, for example, such as critical exponents? So the relations that govern the divergence of the magnetization for an original and a renormalized system are given by these expressions, which can be equivalently expressed in terms of the correlation length. And by dividing these expressions, taking the natural logarithm and linearizing the renormalization group with a L'Hopital rule, we are able to obtain these expressions that allow us to numerically calculate the critical exponents. And here are the results. So for the table at the top, we started with a system that has lattice size L equals 32, and we applied this set of inverse transformations until we obtained a system that has lattice size 512. You can see that as the lattice size increases, we have a convergence of the critical exponents towards the Ising universality class, which is exactly what we expect for the two-dimensional phi to the 4 theory. And we then wanted to see what is the smallest lattice size to which we can apply this method. And specifically for this case, it was L equals 8. So we started from L equals 8 and applied the inverse transformations until we obtained a system that has lattice size 512. And again, you can see that as the lattice size increases, we have this convergence towards the easing universality class. So now in the final part of the talk, I want to answer the question, could we ever use the inverse renormalization group to surpass a supercomputer? So how do I define surpassing supercomputers? So for example, could we use the inverse renormalization group to obtain configurations for lattice volumes that have not yet been accessed by supercomputing facilities? So that will be a first step in claiming that we have something of value. And I will also be discussing this in the case of the three-dimensional Edwards-Anderson model. So I'm going to oversimplify everything. So in this system, we have a symmetric phase, which is the paramagnetic phase, and the system is allowed to evolve in terms of disordered configurations. So at each step, we can have a different disordered configuration. And the moment that we break the symmetry of the system, we cross to the spin glass phase, where the system is able to freeze to a certain configuration. And as you can see, the order parameter of the system is non-trivial. It is not the magnetization. And in fact, in order to describe the order parameter, I have to go to replica theory, which is something that I'm not going to discuss today. But what I want to discuss is how computationally difficult this problem is. So first of all, the Metropolis algorithm does not even thermalize in sufficient time as we approach the spin glass phase, so we can't really use the Metropolis algorithm. Cluster algorithms are not efficient in 3 dimensions, where in 3 dimensions we have the finite temperature phase transition, so we have to resort to parallel tempering or replica exchange techniques. So what this means is that we have to create, as Julian mentioned before, a chain of Monte Carlo simulations that reach until the spin glass phase, and we need to be exchanging configurations, which is exactly what you can see at this figure depicted. So let's say that for L equals 16 in 3 dimensions, I need 20 Monte Carlo simulations. But the problem becomes far more complicated because the system has probabilistic coupling constants, and we need to simulate a large number of realizations of disorder to calculate expectation values. So what this means practically is that if we go to this lattice, the Jij are drawn from a probability distribution. So I first need to sample a set of Jij, and then I need to do 20 Monte Carlo simulations. And then I need to sample another set of Jij and do another 20 Monte Carlo simulations. So let's say that we need 1,000 Monte Carlo simulations, 1,000 realizations of disorder. So 1,000 realizations of disorder times 20 Monte Carlo simulations, we need 20,000 Monte Carlo simulations. And we also need to be simulating multiple replicas. So we need at least 2 replicas, so 40,000 Monte Carlo simulations for L equals 16 in 3 dimensions. So I hope that I have convinced you that this is a difficult problem. And there exists a collaboration called the Janus collaboration, which has access to special purpose supercomputers which are constructed exclusively to study spin glasses, and this collaboration has only managed to equilibrate or thermalize lattices up to L equals 40. So we thought that maybe this is a good problem to see if we can apply the inverse renormalization group. And we have actually, at the moment, succeeded in constructing lattices up to L equals 128, which you can see here. So these configurations are actual configurations obtained from the inverse renormalization group. So we hope that something similar can also be done for problems in lattice field theory or other problems in condensed matter physics. So to conclude, I have answered these questions: how to generate configurations of systems with larger lattice size without critical slowing down effect, how inverse renormalization group flows emerge in a system's parameter space, and how to calculate multiple critical exponents with the inverse renormalization group. And finally, I have also briefly discussed applications of this method to computationally hard problems. So that should be all. Thank you very much for your attention.